Thanks for the invitation. My name's Matthew Penny. I'm at The Ohio State University. I'm there on a Sagan Fellowship, working on supposedly the galactic distribution of planets. But I'm just going to talk more generally about microlensing today, and go through how you find planets with microlensing, and then what some of the selection effects are. Okay, so finding planets with microlensing. Let's start at the very basics, the definitions. I'm going to be talking a lot about sources, lenses, and we're the observer here on Earth. The source is a background star, usually in the center of the galaxy. The lens is another star, usually. It can be a planet, and it can be a planetary system. It will be in front of the source, and usually the source is, well, by definition, you have to be able to see the source, so that's luminance. The lens being a star, it could be a very low mass star, but we can't see. Okay, so how do we get gravitational microlensing? This is the basic geometry of the system. We have the source at a distance here, the lens in between us, and the gravity of the lens will bend light as it passes. So light that would have traveled to us from the source directly will get bent by the lens and not reach us, but there will be other light that wouldn't have reached us, gets bent and reaches us. And you can kind of already see from the symmetry of this process that you'll get rays coming in its direction that reach us, and you can get another ray that passes on the opposite side of the lens that reaches us. So for a single point mass, you get two images of the source, unless the source and lens are directly aligned, in which case you get a single ring-shaped image known as the Einstein ring. And so the equations that describe this, the positions of these images is called the lens equation, and it relates the position of the source, or the angle of the source on the sky, or where it would have been, and where the images are, these thetas. And the scale of this is set by the Einstein ring radius. In this case, it's an angular scale, and it just depends on the distances and the mass of the lens. You can convert that angular scale into a physical scale just by multiplying by the distance. And to put that into context, these are the kind of typical scales of gravitational lensing that we see. I'll start at the right, and that's kind of a cluster lensing. And you've got gigaparsec scales. Maybe the Einstein radius is in a megaparsec regime, and you can see the images themselves and cover a large area on the sky in terms of the size of arc minutes. And if you have a source behind a cluster, you're almost guaranteed to get a lens, see lensing, so that's got a high probability of happening. Coming down in scale, you get galaxies, and distances shrink, and probabilities shrink as well. So the scale is now down to arc seconds, and you might struggle to resolve them if your imaging isn't great. But with Hubble, you can still do a really nice job and see the images of the galaxy, the lens galaxy behind the lensing galaxy. But the probability is lower. Only about 1 in 400, I think, is the number of galaxies is lensed. So then down to microlensing, and this is stars. The reason why we call it microlensing is the angular Einstein scale is hundreds of microarc seconds. So that's where the micro comes from. I've just put milliarc seconds here. But the distances involved on the order of kiloparsecs. The galactic center is 7 or 8 kiloparsecs away. And the Einstein ring radius you get is of order AU, and we'll go into exactly how many AU that is in a minute. But now the probabilities are really low, so we're down to 10 to the minus 6 probability, so 1 in a million. So a bit more detail on the actual scales. So masses of stars, typically that's half a solar mass, maybe a bit lower for the most numerous M dwarfs. If you plug that into the distances as well, the lens is 6 kiloparsecs, the source 8 kiloparsecs. you get a typical scale of about 2 to 3 AU, which, if you're interested in planets, that's an interesting number, because that's where Mars is at 1.5 AU, Jupiter's at that kind of distance. This is interesting. We can maybe see if the planets in a star system will have an effect. Microlensing is also transient, so it doesn't take a star very long to move an AU. Typically, it's the timescale of a microlensing event for the proper motions typical for the bulge comes at about 25 days, which means that you need to keep searching to find microlensing events. So this is now showing the 2 images. So rather than having the geometry stretched along this line of sight, we're now looking down the barrel of the gun and seeing what the source and lens positions are and the images. And so because they move, the source will move from one side to the other side, and the images themselves will move too. One will start out close to the position of the source and trace out, always stay outside the Einstein ring, and can become very large when the source is very close to the lens. The other image is always inside the Einstein ring, and starts off very, very small, but can become large again once the alignment between the lens and the source is small. These images aren't the same size as the original source. We can't resolve them, but because they have different sizes and surface brightness is conserved, it means you get a magnification. And so if you do photometry of a microlensing event, you notice that the background source will appear to get brighter and then fade in a symmetric way. The point lens is circularly symmetric, so you get a symmetric light curve. And the equations governing the magnification are pretty simple. I won't go into them now. And so this is an actual microlensing event discovered by the Ogle survey. It's run-of-the-mill. Ogle finds thousands of these a year now. But you can basically read up for parameters from a light curve. The time scale is a bit like the half of the full width half max. Not exactly, but close enough. You have the time of the event and you have the impact parameter. And so that's basically the inverse of how magnified it gets. Once you get an impact parameter of 0, you should formally have infinite magnification. But because the source isn't a point source, it actually has some physical size that gets washed out, and you have a finite magnification. So energy is conserved. And the only parameter of this event that contains any interesting physical information is the time scale. It's a product of the angular Einstein ring radius and the proper motions. And so you've got the mass, the lens distances, and the unknown proper motions that are contributing to this time scale. So it doesn't contain much useful information at the moment. Okay, on to planets. So what if we put a planet where one of the images is going to be? Then that planet also has mass. It will lens the image that is passing by it as well. And so your nice symmetric light curve gets broken by an interesting feature from the planet. And this is how we're going to find planets with microlensing. I'll move on to something you can actually see with your eyes. That's a bit small. So the way we think about this and conceptualize when you will see a planetary signature, it's important to understand the concept of caustics. And so these seem complicated, but if you look in your coffee mug under a bright light, you'll see one. Sadly, I don't have an image of it here. They're just a concentration of light rays, essentially. In this case, it's slightly different because it's when you trace back rather than trace forward where the light is coming from, but it's essentially the same concept. And so caustics occur when you have more than one body in your lens. And the size and shape of them is going to be important. So they take on some weird shapes, sort of curves which meet at cusps, and then these plots here are actually magnification maps. So if you measured how bright the lens was at any given position, this map is telling you how bright the microlensing event will be. But it's the caustics that sort of dominate these magnification maps for binary lenses. So there's three regimes of caustics. When the separation between, so there's two basic parameters. We have the mass ratio of the two bodies in the lens and the projected separation in units of the Einstein ring. And these two parameters determine what kind of caustics you have. So there's three regimes for a binary lens. It gets more complicated if you have more lenses. But if the planet is within the Einstein radius, then you get three caustics. If it's roughly at the position of the Einstein radius, you get one big caustic. And if the planet is outside the Einstein radius, you get two caustics like this. And it's these properties that set microlensing's sensitivity to planets. So the red dots here are the lens positions, and on the left is always the star, the host star. And you'll notice that there's always a caustic close to the host star, which makes microlensing, which is a very important thing if you want to search for planets and have limited resources to do so. So microlensing takes place over about a month. That means if you are quick at reducing your observations, you can see that a microlensing is happening and start one. So you can use low cadence observations to realize that a microlensing event is going on. You can maybe predict that it's going to go to a high magnification, which means that the source is passing very close to the center of the lens. And then with the fact that there's going to be a caustic by the center of the lens, if there is a planet, you are essentially guaranteed to find the planet if you can monitor it over this high magnification peak. And the trouble is, the size of this region, these are fairly large caustics. They're usually much smaller for planets. Means that you have to have a very, very rare alignment of the source and the lens to be able to see these caustics. But when you do and you can predict it, you can essentially guarantee yourself that you give yourself 100% detection or close to 100% detection efficiency on a planet. And this is how the early microlensing surveys tended to operate, or at least one mode that they operated under was to search for these high magnification events and then throw a huge number of observers, usually amateurs as well, with small telescopes. These get really bright, to densely cover the event and search for a planet. And this is one case where it was successful. You can see the really minute cadence coverage over the peak of an event. And there's slight deviations from what you'd expect for a single point lens microlensing event. It tells you that there's a planet there. But there's not just central caustics, there's also planetary caustics. So going back to the three kinds, there's the resonant caustics, which are always one large caustic near the center, but further in and further out you always have this central caustic, but there's also these planetary caustics, which you can detect planets if the source passes over one of those as well. So these evolve with the different separations and the mass ratios. So lower mass ratios, you get smaller caustics, and larger separations that are very different from the Einstein ring, you get smaller caustics. But the position of the planetary caustics can tell you a lot very easily about the planet that you're seeing. So the location of the spike in the light curve tells you where the planetary caustic is. So just measuring this offset, which you can essentially do by eye, tells you roughly where the planet was, and then the duration of the planetary event tells you roughly how massive the planet was. And so this is the sort of poster child of its kind of planetary microlensing event. Unlike the high magnification events, you don't know where these planetary caustics are. You can have trajectories that look for a single lens, you can have a bunch of trajectories at different angles that produce the same light curve, so you've got no way of predicting when the planetary caustic crossing will happen, if it will happen. So you need to devote more resources to finding these things. But once you do find them, they're very easy to analyze. So if we want to design a microlensing survey to find planets, then we need to run through what we need. So if we wanted to find, say, 10 planets a year, we'd need to know the detection efficiency. I'm going to run through some things later to estimate that roughly, but the numbers here are for Jupiter-mass planets, it's about a 10% efficiency. For Earth's, it's lower, roughly 1%. So now to find 10 planets, you need 100 and 1,000 events. And then you need to know how many stars you need to monitor. The rate at which you get microlensing events is roughly 1 event per 100,000 years per star. So that tells you need to monitor tens to hundreds of millions of stars. To get that number of stars in any reasonable area, you need to go to the densest parts of galactic bulge, where you get 10 to the 7 or 10 to the 8, depending on how good your resolution is. To get 10 to the 8 per sort of 1 degree, you need space-based resolution. But from the ground, you can get 10 to the 7. As I said, they take about a month, or the time scale is a month, so you need to monitor for several months to see the whole event. And then the planet duration is pretty short. So it scales as the square root of the mass ratio, which means that for a Jupiter mass planet, well, let's say Neptune, 10 to the minus 4 mass ratio, that's 10 to the minus 2 time scale, which means you're down to less than a day duration for the event. So you need to monitor fairly rapidly to even catch a planetary event. And then, as I said, you need to do this over several square degrees. So this is a pretty challenging observational feat. So the first attempts were there are other surveys that did microlensing searches, but the main leaders in the search for planets were MOA and OGLE collaborations, and they used images that were initially less than a square degree across, or less than a square degree field, and they monitored many fields. They couldn't get the cadence to find planets themselves, but they developed real-time reduction systems to be able to alert microlensing events. Then once the microlensing events were found, this greatly increases your chances of finding a planet if you just need to monitor individual events. So they did this for several years each, and they found a bunch of planets in this sort of survey and then follow-up mode. There was one team that just went after high magnification events, and others that went after lower magnification events with the lower probability, but more events. This was the first microlensing planet that was found. It actually didn't need any follow-up, which is surprising. It was like there wasn't another planet found in this way for many years until the surveys had been upgraded. Then there's this very low mass 5 Earth mass planet that was found in 2005, which was, I think, maybe close to the lowest mass planet at the time that had been found. Maybe it wasn't quite the lowest, but And then there was this double planet system that looked just like a scaled down version of Jupiter and Saturn around a half solar mass star. The surveys have been upgraded in that time. They now have square degree scale images, so they can now start to find planets themselves. They survey small areas at very high cadence, sort of 15 minutes, which is much shorter than the timescale of a planetary deviation from a microlensing event. So they can search for planets themselves. And just online this year is KMTNet, which is kind of doubles the size of the images and with bigger telescopes too. It's kind of a pinnacle of the ground-based microlensing surveys. And these are the kind of planet discoveries that you get from just surveys themselves. I think in both of these cases there's actual follow-up data too, but the planets can be found by the surveys themselves. And this makes understanding your detection efficiency much, much easier. You no longer have human decisions in the pipeline that you need to model, especially when those human decisions are usually via email communication that you need to go back and piece together the history. Now you can just blindly search for a planet, and when they show up, you can easily add them to your sample of planets. And if there's no planet, that also is easily added to your denominator. And so this is the state of microlensing planet discoveries so far. I've plotted them with mass and semi-major axis estimates. These aren't oftentimes the mass estimates are, as I say, just estimates. Some are measured, but the semi-major axis isn't measured in the event. But you can see that they're probing a different parameter space than the rest of the planet finding techniques. So we've got radial velocities finding things up here. Kepler's finding small planets at smaller radii, and then you've got direct imaging planets here. But this sort of region here is being probed only by microlensing at the moment, and will be for the foreseeable future. So back to the selection effects and how we end up with planets in this region. So there's we can split these up into two groups. One is the hosts themselves. You don't get to choose which star has a microlensing event. So there's selection effects that go into that. Nature does it for us. And then there's the planets that affect things as well. So each star, the rate of microlensing events will depend on basically that will determine the distribution of host star properties that you have. And so as I discussed earlier, it depends on the mass and the distances of a planet and the proper motions. The mass is of obvious interest, but the distances and proper motions are as well, because we're looking towards the galactic bulge through the galactic disk. These are two different stellar populations. They have different ages, different metallicity distributions. So there's potential to discover interesting things about what planets form in what conditions, what are the starting conditions you need, that can potentially be answered by microlensing, because they probe a range of different planet properties that might not be probed by techniques that are forced to look in a much smaller volume of sort of more local to the galaxy and just the disk. So this results in a sort of 60-40 split in the position of the lenses. 60% are roughly in the bulge and 40 in the disk, which is kind of ideal for statistics. You want a roughly equal split between your two samples. But there's some more complications, which I won't go into, but because the Einstein ring radius depends on distance, that means you're looking at different planets at different separations. So you need to take that into account when you do any kind of study. The mass is important. So many people think of microlensing as probing just M dwarfs, but microlensing is more sensitive than average to more massive stars. This is because Einstein radius scales as the square root of the mass, so you have a bigger Einstein radius, you have a bigger cross section, that you get more events. So it tilts the IMF from being quite steep to less steep, and it means that roughly 25% of lenses will be solar. This is just main sequence stars. Roughly 25% will be in the typical range that we search for transits and radial velocities around. But then it's still dominated by M dwarfs, but it's a nice, nearly equal logarithmic spacing in mass, which can be pretty powerful if you want to study the dependence of the abundance of planets as a function of host mass. But unfortunately, we don't always get the information on what the mass of the lens is. Often it's dark, and even if it isn't, it's completely coincident with the source star that can't be resolved. So you either have to wait a very long time for them to separate, and then that's of order 10 to 20 years, or there are some rare. If you have a long event, you can use the motion of the Earth to get a parallax. Essentially, I won't go into the details, but that can help give you some information on the distance and hence the mass. And in recent years, Spitzer last year and this year has been observing microlensing events and getting satellite parallaxes, which are much more likely to yield results and much easier to understand. And next year, K2 will do this on a new scale again. Okay, so back to the planets. What effect do they have? What are we selecting for here? So, caustic size is a function, as I said, of mass ratio and projected separation. Turns out that these are pretty nice dependencies on size. The planetary caustics go as the square root of the mass. This is kind of expected. The Einstein radius goes as the square root of the mass. So that's a nice shallow scaling compared to other techniques. Radial velocity, it goes as the mass. Transits, I think it goes even steeper if you incorporate a mass radius relation. The central caustics go as the mass, which means that they shrink much quicker, and your high magnification events are only probing a smaller range of planet masses. But that's still a pretty large range, from maybe a few Earth masses up to anything larger than that. And the resonant caustics scale even less steeply with mass ratio. So, but there tends to be they're not quite as useful as that suggests, because they tend to be relatively weak, and you need very good precision photometry to see very low mass planets through resonant caustics. Okay. The position, as I said, depends on the separation, and only on the separation, projected separation, which is a nice property. So it means that when you see a planetary caustic perturbation on the light curve, you can essentially read off where the planet is. And there's, again, some relatively nice scalings on how the caustic size goes with projected separation. So it goes as squares, which is not quite so nice. It means that once you move away from the Einstein ring, you get a fairly steep drop off in sensitivity. This is really bad when you get to close lenses. So with these small caustics, they drop off not as the squares but the cube. So you quickly lose sensitivity at small separations. But it's not so bad when it comes to wide separation planets, because once you move your planet away from the star, it's just a mass on its own, and a mass can lens just as well as any other. And so you can still detect planets at any separation. Just you might not know whether it's bound to anything or not. So now we're talking about free-floating planets, which is another topic of a lot of interest, but I'm not going to go into. There's another effect to consider as well. So this is part of the reason why if you have the planet but it's perturbing the image that stays close to the source, it stays relatively large and doesn't shrink, doesn't get any smaller than the source. So yes, you can detect the planet at any position, but inside these images get really small really quickly, and that's why you can't detect planets that are very close to their stars, because they're basically not contributing any light to the microlensing event by the time they're too close in. So putting this onto sort of a sensitivity curve, I need to explain what a microlensing sensitivity curve in this kind of mass semi-major axis or mass ratio projected separation space is. It's not quite the same as the typical curves you're used to seeing for Kepler or radial velocities, where you have a region of nearly 100% sensitivity, and then it quickly drops off to zero with a relatively sharp edge. With microlensing, it's a continuous sensitivity map. There's only ever 100% sensitivity for high magnification events, but low magnification, you've only got a relatively low probability of detecting a planet in any one given event. So the lines on these plots typically are drawn at the position where you would, if you have one planet per star on that line, you would detect so many planets per year. This case here isn't really showing that either. I've just put the lines at an arbitrary position to show the kind of scalings that you get in this mass ratio projected separation space. Putting it into units you're more familiar with, mass and semi-major axis, you get a broader spread because you can have a range of Einstein radii, which multiplies by your projected separation. And so you get these contours. So these are the contours of constant planet detection rate if you have a given number of planets at that position in the space. But it gives you a sense of where you will find planets with your microlensing surveys. And so I've drawn on here KMTNet, which is the new upcoming ground-based microlensing survey, and WFIRST, which is the space-based survey that will be launched next decade, maybe in 10 years or so, maybe a bit less. And you can see that ground-based are getting down to about 1 Earth mass, but space-based surveys are going to go much lower. You can ask me about these planets later. Okay, so how would we, if we do a microlensing survey, how would we go from the detections to understanding the planet population that we're probing? So it's essentially another case of brute force wins the day. You basically want to inject planets into your microlensing event and see if you recover them. It becomes a bit more brute force when you have a relatively low probability of detecting the planet in any given event, so it can be quite computationally expensive. And there's a bunch of nuisance parameters you need to marginalize over, like when the event happened, how long it was, the impact parameter, things like that. But you can, if you marginalize over those, you can produce a map of detection efficiency as a function of the interesting parameters, the projected separation and mass ratio. Turns out it's slightly easier than that. You know most of these parameters from the underlying microlensing event, and you can get some of the others as well. But you do need to marginalize over the angle of the source trajectory, the angle that the source takes relative to the planet-star separation axis. And this lets you produce maps like these, which tell you if you have an event that doesn't seem to have a planet where you're guaranteeing that there's no planet. And these are always probabilistic. The shading here goes from, I think this is a high magnification event, so it goes from 100% to lower probabilities. But there's a region where you can guarantee yourself a detection of a planet if that planet exists. For lower magnifications, it covers a much smaller region. Are we done? Yeah, I'm close. Yeah, and so these are, I'll skip over that, but these are the more typical detection probability plots that you'd see for transiting planets. And these are the kind of results that we've got so far with this. Going from measuring the mass function of planets beyond the snow line, and we found free-floating planets. And I'll stop there. Okay, so the question was, what's going on with these detection maps? It's mainly coverage, so observational coverage. If you observed the event perfectly with uniform cadence covering the entire event, they would be more symmetric. They wouldn't be completely symmetric because the quartzics aren't circularly symmetric. You get these spurs of higher magnification that come off them. So you would get, it would be more symmetric, but not completely symmetric.
Yeah, are you excited about K2 campaign 9, and what do you expect to find?
Okay, so the question was, am I excited about K2 campaign 9, and what do I expect to find? Answer, yes, very definitely. So a bit of background, campaign 9 of K2 will be looking towards the galactic bulge. Rather than doing the normal Kepler thing of picking stars to target and just downloading pixels around those, campaign 9 will download a huge 4 square degree block of pixels right where the microlensing event rate is highest. That should allow you to detect around of order 100, maybe more. We're not quite sure. We don't know how well we can do with the photometry in these dense fields with 4 arcsecond pixels, but of order hundreds of microlensing events. And if you observe simultaneously from the ground and space, as Kalen mentioned in his POP, you see a different microlensing event. And the difference that you see and your knowledge of the baseline between Kepler and the Earth allows you basically to get a measure of the one projection of the microlensing event, which tells you about the distance and tells you constraints and mass as well. You can use some other constraints to get more information and completely break the degeneracy, which gives you the mass and the distance. This is exciting for planetary events, but the unique thing that K2 Campaign 9 will let you do is it doesn't need any follow-up, and you can do this for very short microlensing events that you wouldn't have a chance to maybe send Spitzer to look at. And these are the events that are caused by free-floating planets. And so it will basically allow us to prove or refute whether the free-floating planets that have been discovered in previous microlensing surveys are planetary mass objects. It won't quite say definitely that they're free-floating planets, but that can be left to later, as Kalen explained.